In the previous video, I showed you a very useful theorem in that whenever this thing here has a limit, and the limit of this tends to 0, then overall the whole limit here does not exist. So in this video, we're going to try and prove this. There are lots of ways of proving things in mathematics. One way is to use proof by contradiction, and that's what we're going to use to prove this here. So with proof by contradiction, we set up a statement, our initial statement. Our initial statement is that this here has to have a limit, and the limit does not equal 0. So so our initial statement here is L1 exists. Okay. Now, in order for us to have a theorem at all, we insisted that that this has to have a limit, and that limit cannot be 0. That's in order for us to have a theorem at all, we insist that this must be true. This thing here has to be true in order for us to have a theorem at all. Okay, so so with proof by contradiction, we set up a statement here. L1 exists. Okay, and then when L1 exists, we have a hunch that this thing here, f of x here. Hang on, bear with me. So we proof by contradiction, we set up a statement which we insist to be true, because in order for us to have this theorem at all, this thing has to be true. Okay, so this statement has to be true. Now we have a hunch that when this is true, the limit of this here does not exist. But with proof by contradiction, well, we have a hunch that this is the limit of this here does not exist. But proof by contradiction, we say, okay, let's just say it does exist. Let's say the limit of this does exist. And the minute we make this statement that it does exist, then this thing here breaks down. L1 will break down. Okay, so with proof by contradiction, we start out by making a statement. Okay, in that we insist that this has to have a limit other than 0. Now, when this is true, inside our heart, we know that this here does not have a limit. Okay, this here does not have a limit. But proof by contradiction, we say, okay, let's just say it does have a limit. We say the opposite. So let's just say it does have a limit, and then the minute we do that, then this thing here breaks down. The minute we make the false statement here, this thing breaks down, and then we will have no theory at all. So this by saying that it does have a limit, we don't have a theory at all, because our initial statement breaks down. That's the general gist of proof by contradiction. So let's just follow this through. So we remember, in order for us to have a theorem at all, we insist that this must always be true. It must always be true. This thing here has to have a limit other than 0. Okay, we must always hold. We need to insist this for us to have a theorem at all. Okay, so that's what this statement here is saying. Suppose the limit of f of x here, suppose the limit of this exists. Let's call it L1, and it doesn't equal 0. Okay, and so we made a statement that L1 exists. Okay, and then, well, inside our heart, we know that this here, the limit of this doesn't exist. But with proof by contradiction, we say, okay, let's suppose that this thing here does have a limit. Okay, hang on. So we're saying that, okay, we know deep down that this does not have a limit. But let's just say, suppose further that this thing here does have a limit, and it does have a limit here, and it equals L2. Okay, so we are saying, okay, let's just say deep down we know that there is no limit. The limit doesn't exist. But we're going to make a statement that, okay, let's just say the limit here does exist, and that limit is L2. Okay, so this thing here has a limit of L2. Now look what happens. So we start out with our f of x here is this. Well, f of x here at the moment has a limit of L1. Okay. Well, we're going to rewrite f of x as this, g of x times this thing here. Okay, so because these two will cancel out, so we're going to say f of x. We're going to say f of x equals this thing times this thing. Now, whenever you have two things multiplying together, then you can say the limit of this thing times the limit of this thing. So in one of the theorems, you've got two things multiplying each other here, so we can actually break them apart and just work and concentrate on working out the limit of this, and then work out the limit of this, and then multiply the two together. Okay, and then g of the limit of g of x. Don't forget, in our initial theorem, we stated that, okay, we did state that the limit of this is has to be L1, but then we also insisted that g of x, the limit of g of x is 0, heads towards 0. So, well, if that's the case here, then the limit of this here is 0 here, and then suppose, well, this thing here, hang on, bear with me. We started out by saying that L1 exists, and deep down inside our heart we know that this here does not have a limit. Okay, but to use proof by contradiction, we said that, okay, let's just say this thing here does have a limit, the limit of L2. That's why this thing here equals L2. Okay, and now 0 times L2, that gives you 0, meaning that L1 here, the initial statement L1, the L1 is 0. But then going back to here, we insisted that L1 has to exist. It cannot be 0. It cannot be 0. So I know this it's tricky to understand proofs in math. So you might have to watch this video again and again and again. Okay, we started out by looking at the limit of f of x. Okay, so we rewrote f of x as one thing multiplying another thing, because these two, well, this thing here is in effect f of x here, and then and then it turns out that the whole thing here, well, whenever we made this statement here, hang on, L1 exists, and then whenever we made this statement to be false, then L1 we are forced. If this is here is false, we are forcing L1 to be 0. But then we insisted that L1 cannot be 0, so it contradicts the whole thing. So we cannot make this statement here. We cannot say, oh, this here has a limit of L2. We just cannot do that. The minute we do that, then we are forcing L1 to be 0. But then L1 has to be something in order for the theorem to hold. Okay, you just have to watch this again and again and again, like I did when you just got to read it again and again and again in order for you to try and understand it. How? So here, this is our initial theorem here, okay, and the proof is as follows. I'm just going to scan through it. So you're just going to have to press pause and try and understand it for yourself. Okay. Okay. You okay. It doesn't matter if you don't understand this. Just try your best to try and understand it. And when you're older, then if you still don't understand it, when you're older, then come back to it and reread it again. Maybe a year or two later, or a few months later. Okay, just try your best. I'm just going to scroll through this once more. So this here is our statement here, our theorem here. Okay, and the proof is this. Just try your best. If you don't understand it, then come back at a later date. Okay.